All right, so welcome to Constantine's thesis defense. So Constantine, I guess, what, 2015, I think, is when you started. Is that right?
Yeah.
Yeah. So like all things before COVID, that feels like this sort of some kind of distant history at this point. So not only will today be a big day for Constantine personally, but this is also the first thesis defense for the new PhD program. So the PhD in physics, statistics, and data science. So as long as you don't stuff this up, you're going to be the first person to receive that degree. So that'll also be a big moment for MIT and for Jesse and I who pushed this through. So Constantine, over the last 5 and something years, has been working on searching for what are called dark photons, which I'm sure he'll explain, potential force between dark matter particles, but also doing a lot of machine learning and AI work, including an internship working on Amazon Alexa over the last summer. And that is the direction he's heading after this, going into data science. And so, all right, go ahead and tell everyone all the wonderful work you've been doing for the last 5 years.
Sure. All right. Thanks all for being here, and thanks for the nice introduction, Mike. So in this talk, I'm trying to bridge the gap a little bit between the world-leading science results that will hopefully warrant a PhD for me, and on the other hand, kind of sharing with the more non-technical folk on the call a glimpse of what gets us excited about both particle physics, as is symbolized by this thing on the right here, and machine learning. After all, that's what I've spent the past 6 years of my life doing. And I think, given that we have quite a few people on the call now, I think it might be easier to take questions at the end. But if you have something that is very urgent, just send a message in the chat or something. All right, so let's start with particle physics and the motivation to look for these dark photon particles that Mike also mentioned. So let's start from the beginning. What's the motivation? So the universe is expanding at an ever-accelerating rate alongside space itself, and is cooling in the process. And so that suggests that the universe was denser and hotter in the past and originated from the Big Bang. And simulations of this expansion and the galaxy dynamics show that this behavior of celestial bodies observed by telescopes can only be achieved by the presence by this extra gravitational pull from an unknown substance. And we know that the substance does not interact with the strong or electromagnetic forces of the modern baseline model of particle physics, which we call the Standard Model. So this is why we can't just directly observe this substance with telescopes. That's why we call it dark. And when we look at two clusters of galaxies coming together and colliding, seen in a spolar cluster here, we notice that ordinary matter in the form of gas, which is shown in pink here, is slowed significantly by this collision. And that's as you would expect. However, most of the mass is actually concentrated outside of this region, where this ordinary matter sits, and is shown here in blue. So this tells us that this unknown substance is in some way localized. And that's why we call it matter. And this dark matter makes up 85% of the matter in the universe. And finding out exactly what it is one of the most sought after goals in particle physics, and something I've been working on. So there are many theoretical attempts at solving this problem. And the Standard Model is based on the symmetries. So for example, to incorporate the dark matter, there could be a larger symmetry group like supersymmetry or something that encompasses the Standard Model of particle physics that we already know, in addition to yet unknown particles and unknown stuff. And in that case, we could produce dark matter particles through interactions of regular matter. Although these models look very appealing, or looked very appealing, a lack of discoveries, both at the LHC and direct detection experiments, suggest that we should start thinking about something else. So what if we're not so lucky as to have the simple extension of the Standard Model in which dark matter particles can be easily produced? What if there's a rich collection of dark matter particles, which we call the dark sector here on the right. And there's no connection between the standard model on the left and the dark sector on the right. In that case, this dark matter could easily evade being detected in modern particle physics experiments that are designed to test increasingly high energies. So these two sectors are disconnected. Does this mean we have to give up and there's nothing we can do? A simple possibility is that this dark matter interacts with itself via a new force, shown on the right here, by a so-called Feynman diagram. So you can read it as you have two dark matter particles coming in, interacting with some kind of dark matter force, and two dark matter particles coming out. And this kind of force is similar in structure, at least, to the known forces, like electromagnetism that we already know. And so in physics, forces of nature can only really act at a distance. So they cannot act at a distance. So they need messenger particles, or so-called force carriers that attract or repel. So for example, if you have two negatively charged spheres, they repel each other by exchanging force carriers. And for electromagnetism, the force carrier is a photon. And for this dark electromagnetism, the force carrier is called a dark photon. But still, until now, the standard model and the dark sector don't interact. So that makes it difficult to produce dark matter and study it in the lab. However, if particles exist that are charged under both the standard model and dark sector forces, even if their masses are very high, then you can fuse the left-hand side here of the standard model diagram and the right-hand side of the dark matter diagram with the so-called loop in the middle together. And this creates what's called a portal between the standard model and dark sectors. And this is allowing us to look for a hint of dark matter, even in this pessimistic scenario where dark matter is not charged under standard model forces. Out of the different options of these portals, the dark photon portal is the most viable option for thermal models of light dark matter. And when this dark photon is lighter than twice the mass of the lightest dark sector particle, then there's just not enough energy to decay to two dark matter particles. So it has to decay to ordinary matter. This is what we call visible decays and is what I'm going to be concentrating on here. And the dark photon couples to standard model particles via the electromagnetic current. So its coupling is suppressed relative to that of the ordinary photon by a factor, and we call that factor epsilon, and it's one of the two free parameters of this model. Think of epsilon like a measure of how often this dark photon is produced in comparison to an ordinary photon. The other free parameter of the dark photon model is just the mass of this dark photon. So now we have a theory and we want to test it. So for every value of the two free parameters, there are three possibilities. Number one, we find enough evidence that this model is a good extension of the standard model and we can claim a discovery. This means booking a flight to Stockholm to get a Nobel Prize. We would obviously love that. Number two, we find enough evidence against the model to exclude it. Or number three, so we just don't have enough data to make a definitive statement. So for dark photons, there's currently no evidence of existence, but we have excluded certain models. So here, given that there are two free parameters of the model, we summarize the status by a 2D exclusion plot. On the x-axis is the first free parameter, which is the mass of this dark photon, and on the y-axis is this epsilon parameter, which measures the strength of the coupling. So there's been no discovery of dark photons. So every colored spot on this plot has been excluded. Every black spot is uncharted territory. Let there be be dragons here, or whatever they say. And that's what we want to explore with new experiments. Naively, the most interesting region, according to theory, is this white rectangle. So it is set on the y-axis by values of epsilon of 10⁻⁵ to 10⁻³ because of these 1 and 2 loop scenarios, which are favored by theory. An astrophysical consideration set the masses here between 10 and 400 MeV. So we would like to explore the space in this white box. But any part of this parameter space that's yet been unexplored is interesting, even because if the model is slightly altered, this could really be interesting. So if you use the particle collider of high energy, we can also cover this region here in the top right. And in order to cover this interesting region of the white box, we need a lot of data because epsilon is small. And to use this data efficiently, we need to reject all these other processes that we don't want to see, so backgrounds. The LHCb experiment that I work on can deliver on these requirements. And let's see why this is true and why we do all of this proton collision in the first place. So how can we produce these dark photons? So this is more for the non-technical folk on the call also. You've probably heard of Einstein's famous formula E is equal to mc squared, but you might not know what it does. It means that mass is like a unit of energy. So if we accelerate protons close to the speed of light and then we collide them, they have so much kinetic energy that they can create pairs of particles out of nowhere. This is like when 2 cyclists collide and out pops a truck, which is something that just doesn't happen in normal life because we live in a state of comparably low energy, which maybe a lot of us can relate to with COVID. So we need to create an environment with these very high kinetic energies, which existed just after the Big Bang. And that's what we use particle accelerators for, which effectively imitate this environment that was present at the beginning of the universe. And so let's see, and this is exactly what the Large Hadron Collider, or LHC, at CERN does. And here we can just watch a very short film about how it accelerates protons and collides them. There's no audio. So CERN is located in Geneva and is so big that it lies in both France and Switzerland. On the bottom right here, by the way, you can see the LHCb experiment that I work on. So first, protons are extracted from a hydrogen bottle, and then they're accelerated by bigger and bigger accelerators until they reach their maximum energy in the LHC. And the beams cross over in 4 interaction points, which are surrounded by large particle detectors each. Individual protons then collide, producing sprays of particles. And these are recorded by particle detectors, which we also call experiments. And the debris of the collision is then analyzed, and we play detective to reconstruct what processes took place. And this whole thing is a large data science effort. Let's not watch that one again. LHCb is one of the 4 big experiments at the LHC. It's roughly 20 meters long and located 100 meters underground, and is run by an 1,000-person collaboration. Here you just see a small person here for scale against this backdrop of this relatively large LHCb experiment that also Mike had as a background earlier. LHCb only detects particles in a cone from roughly 1 to 15 degrees from the beam axis, which makes it a single-arm forward spectrometer. It has excellent resolution to the lifetime and mass of particles. Also is very good at identifying what type of particle that passed through the detector, and at selecting which crossings of these beams, which we also call events, to throw away and which ones to keep. This process is called triggering and is crucial because we have to throw away a lot of the uninteresting data. So now we will talk about how we use LHCb to search for these dark photons. And that will need a more technical discussion. So most of you should only listen to the first couple of sentences of the next 3 slides and can pretty much sleep for the rest of them. In a few slides, I'll show exclusion plots to show you the results of how it all turned out. All right, so let's get started. So first, I'm going to give you an overview of the searches with data from LHC's Run 2, data taking from 2016 to 2018. So our strategy is to look for both prompt and displaced, inclusive, dark photons decaying to 2 muons. As the dark photon couples to the electromagnetic current, the kinematics of its production and decay are exactly the same as they would be for an off-shell photon of the same mass. Therefore, after making stringent PID, particle identification, geometric, and then other requirements to reject backgrounds, we get a number of signal candidates. We'll compare this number to prediction from the off-shell photon yields. We compare the two to either then set limits or claim a discovery. And because of this strategy, we now have, we don't have to know absolute efficiencies or luminosities and have a fully data-driven search. Just the beauty of this. And to have sensitivity to dark photons at lower masses, we need to have momentum cuts of half a GeV, for which LHCb's flexible triggering scheme is paramount. And then for the prompt search, we also use what we call the turbo data stream, which allows us to only keep the reconstructed information, discard the raw event. This is only possible, once again, to the way we do triggering in LHCb. And due to the smaller data sizes, we can keep more events. That's necessary for this analysis. Okay, let's concentrate on the prompt search. So here, we are looking for dark photons in general, is like looking for needles in a haystack. So there are other background processes that we try to limit that make it harder to find the dark photons. And these backgrounds are already highly suppressed by the cuts we've already made. However, we still have a few more that we haven't completely cut down on yet. So number one, the off-shell photons. This is an irreducible background and is what we will use to normalize our search. Improving our mass resolution by constraining the dimuon mother particle to be prompt actually reduces this background. And secondly, there are resonant decays to dimuons. So we all love our standard model resonances. In the slide, I'll actually show you the dimuon spectrum from threshold to the Z. And we see that I see all of the resonances that we expect. However, these resonances are peaks in the spectrum, and we're looking for a peak in the spectrum. So for this analysis, we vetoed these regions. So now there are 3 types of misreconstruction that we have to worry about. First one is muons from heavy flavor quark decays, which are misreconstructed as prompt. This is estimated by with a binned extended maximum likelihood fit to the minimum IP chi-squared distributions. And so IP chi-squared is the difference in the vertex fit chi-squared when the PV is reconstructed with or without the muons. And in the second type of misreconstruction, 2 prompt hadrons are misidentified as muons. And there's also the case where one muon is misreconstructed as prompt, and the other one is a prompt hadron misreconstructed as a muon. And together, these 2 backgrounds can be subtracted by using a designated sane sign dimuon sample. And approximating these types of misreconstruction gives us an estimate of the off-shell photon yield. Still above a mass of 1.1 GeV, misreconstruction dominates. And we know that at these masses, the off-shell photons are primarily produced by Drell-Yan, and so are the dark photons. And so we apply an isolation cut. So here is a dimuon spectrum that I told you about with all of the bumps at the expected resonances. You can see how smooth it is except for the isolation requirement here applied above the phi. And to just give you an idea of the size of this data set, the eta to mu yield is 300,000 here, which at that time was roughly 2,000 times the combined previous world's data. And this is data only from 2016, which gives you an idea of how much data we have in our full 2016, 2017, and 2018 data set. And actually, after getting this plot, we vetoed all of the regions where the known resonances were. So we don't have as nice a plot for them, but it helps us with the analysis. So we have our analysis is more than 3 times this data set. All right, so for the prompt search, we follow this strategy. First, we obtain the expected number of dark photons. Then we see if we can find evidence that dark photons have been observed. So if we can see that evidence, then we use the expected number of dark photons to compute a significance and possibly claim a discovery. In the absence of evidence, we compute an upper limit on the observed number of dark photon candidates, and if it's smaller than the number of expected dark photons, we exclude this model. We repeat this process for every value of the 2 free parameters, epsilon and the mass of the dark photon. All right, so we compute the expected dark photon yield as follows. First, we get the off-shell photon yield by subtracting the misreconstructed backgrounds as explained earlier. Then there are some known factors which we can calculate. And lastly, there's this efficiency ratio. And if the lifetime of the dark photon is much smaller than the resolution, this factor is just 1 and can be ignored. And the observed dark photon yield is computed by a so-called bump hunt and consists of thousands of automatic fits using a novel background selection method that we can talk about if you want. And for this prompt search, no evidence was found, and we set limits. So here are the results. The limits of the prompt search from near the dimuon threshold here up to 70 GeV. And our search is the one in dark blue, which is the full run 2 search, achieves a factor of 5 better sensitivity at to epsilon squared at low masses in comparison to the search done with only 2016 data shown in turquoise, and a factor of 2 at high masses. And we actually get the world's leading limits to from the dimuon threshold up to 740 MeV, and then from 10.6 GeV to 30 GeV. And importantly, these searches are limited by statistics. That means if we get more data, and we will with the run 3 of the LHC, these results will get better. Okay, let's move on to the display search, the second type of search that we do. So here, there are other background processes that produce signatures like the dark photon. The first one is a bihadron decay chain that produces 2 muons. So we reject this mostly by topology cuts in addition to vetoing heavy favor signatures. It's in association, either if they're associated with muons or even independent of them. Secondly, we have this k short to pi tail, which is pretty huge, even with stringent particle identification criteria. And this limits us to search masses below it. And in even those masses, we have to subtract its background by extrapolation. And lastly, we have photon conversions in the Velo detector. These are rejected by a dedicated material veto tool, which uses self-imaging of the Velo. So for this search, we still use the same prompt off-shell photon yield and the same factors. However, no, this efficiency is no longer 1 because it depends on this decay time t. And we also have a lucid trigger. And we estimate this efficiency with data-driven resampling. For the displaced search, the observed dark photon yield is obtained from 3D binned extended maximum likelihood fits in the muon mass, decay time, and quality of the fit vertex. And once again, no evidence was found, and the most significant excess was 2 standard deviations. Whoops, here you see the 3D fits. All right, so here the exclusion plot for the displaced search. Once again, limits from the 2016 search, from the earlier search were in turquoise, and what's excluded by this new search is shown in dark blue. What's important is that a lot of these regions are actually pretty dark gray, which means they're very close to being excluded. And this slide summarizes the progress we've made with this work in my thesis. And so we set world-leading limits with the prompt search all the way up here. And are the first ones to cover this parameter space in between, and these in the middle intermediate ranges here. And these searches can be actually recast to set limits on slightly different models of other vector particles. And in a follow-up study, we also perform more general searches for peaks in the muon spectrum without requiring dark photon production mechanisms. And this requires computing absolute efficiencies and setting upper limits on cross-sections in bins of mass and PT. These searches, for example, set world-leading constraints on some parts of GeV scale bosons in the Higgs doublet and hidden valley scenarios. But the LHCb detector will collect more data with LHC's run 3 that will happen from 2022 to 2024. And a more than 3 times increase in luminosity is expected. And we also have big improvements in the trigger and offline processing, which will improve the sensitivity beyond the sample size. For example, we have this hardware level trigger that will be removed. Overall, we will see a factor of 100. We expect an increase of a factor of 100 in this search here, this place search, in comparison to this run 2 data sample. And given that large fractions of this parameter space, shown in this previous slide here, would already be excluded if we had 3 times the amount of data, having 100 times the amount of data will hopefully make a big difference. All right, and so I'm going to summarize the first part of this talk here. And so dark sectors are dark matter scenarios that are worth exploring, and LHCb has world-leading sensitivity to different models. All right, we're going to switch gears a little bit because I'm at least trying to get a PhD in physics, statistics, and data science. And so we're moving on from this dark photon search. And I'll give you a small flavor for some of the machine learning statistics I did for my thesis. So there are 4 topics that I worked on. So number 1, we created MODE, which is a fast and easy general method to flexibly control machine learning classifier dependence on a continuous feature. And this approach is very helpful to prevent biasing in particle physics analyses while retaining classification power. But it could also be applied to constrain, for example, applying it to COVID, the COVID vaccine distribution fractions to be at mostly quadratic in age. This work was shown at NeurIPS 2020, for example. The second project was we created high precision generative model approaches to high energy physics simulations, which was shown at ICLR 2020. And my collaborators and I in this project 3 developed a simple, powerful, and novel deep learning approach to vertexing, which is a technique to determine the location of vertices of sprays of particles given particle tracks. And lastly, we put the pedagogical paper on the archive using machine learning classifiers for goodness of fit and 2 sample tests. Today here, I'm going to quickly talk about the second project, namely generative models for particle identification. All right, what is the motivation? Why do we care? In order to perform these physics analyses that I showed you before, and physics analysis in general, we need simulation, which we in particle physics also call Monte Carlo. And producing this Monte Carlo is very computation heavy. And here you can see in green how much CPU power is needed to perform these physics analyses well. The red line shows you how much CPU power we will actually get. This is what we want. This is what we have. There's a big disconnect. Hence, we need a fundamentally different approach to generate simulation. So currently, the standard approach is to generate what happens in the particle collision, then follow these particles through our detector and simulate all of the interactions these particles have with the detector, which we call microphysics. And then we also reconstruct what we see. So this is, which is exactly what we would do if we saw real data. From that, we compute these particle identification features that tell you the likelihood of a particle being of a certain type, for example, electrons, muons, and so on. This is done in exactly the same way as you would in real data. This is the standard path. But this path takes a lot of computation time. And the question is, can we take a shortcut? So the plan of this project is to generate these PID features directly from the decay products with the use of machine learning and generative models in particular. So to test if the simulation works, we estimate the difference in performance between using original Monte Carlo and a machine learning simulation. So for this, we use lepton flavor universality measurements, which is a high profile physics analysis. It's actually so high profile that news sites like the BBC and The Guardian just published stories last week about the discrepancy to the standard model of a new version of this analysis. And I can send you the link if anyone is interested. All right. So machine learning, what's a generative model? Let me show you. These people don't exist. They were all made by a generative model that has looked at many faces and has learned what we consider to be a face. And we want to do something similar, but for particles. And we have this site here, thispersondoesnotexist.com, that you can visit if you want machine learning to generate some new faces for you. And these will always be you. And they're very high fidelity, but there are some mistakes that are being made. So if you pay close attention, for example, what the hell is going on with this hair? It's just a little strange here. So there are many types of generative models. And in this task, we care very much about sampling from the whole distribution of PID features, rather than producing a few high fidelity examples as these pictures of faces that we just talked about. And that is why we use normalizing flows, which is a generative model with tractable distributions. It allows for efficient sampling and density estimation. So the way it works is we have a simple distribution, like a Gaussian, and we transform it into our target distribution by a sequence of invertible and differentiable mappings. And the prior imposed by these mappings will help produce smooth distributions. And here are the results. They might not look as fancy and nice as the fake faces that I showed you, but the results matter to us. So in the top here, in blue, you see the one-dimensional distributions we try to approximate. So we want to get to the blue. And the orange is what has been generated by our model. So this is not, so here we try to produce a three-dimensional data point. And in the bottom plots, you see the two-dimensional distributions. Once here on the left, this is what we generated. And on the right, this is what we want to be like. Once again, even more difficult structures like this are pretty similar in both of these. this is good. And this is my conclusion slides for the machine learning part. So what matters in an analysis for us is how we can use these PID features to select data. And this is measured by the cut efficiency. If we want the cut efficiency of our generative model to be the same, we want our cut efficiency of our generative models to be the same as for the traditional geant, not less or more. And they want it to be the same for a variety of every value of different features. So perfect equality, which is what we want to get to, is shown by this light gray dotted line here that's horizontal at 1. A dumb model, shown in gray here, reaches values of 1.17, which is pretty far away from 1. So if we move further away from 1 than this, then our model is extremely bad and we should just stop working on it. A GAN model, which is like something that was used for the faces, results in this blue line here, which is pretty close to 1. But our flow-based model, shown in orange, does even better and is pretty consistent with 1. So that means that it would be, it looks like it would be acceptable to use flow-based simulation for this analysis rather than the traditional geant. So for that reason, flows have the potential, at least, to revolutionize the way we generate simulation at LHCb. So that wraps up the machine learning portion of the talk. So today I've told you about the search for dark photons at LHCb and machine learning in particle physics. I hope I managed to get you excited about what I've been excited about and showed you what you can achieve when we use machine learning to push the frontier of particle physics. And yeah, thank you for listening to my talk, and I'm open to questions.